Okay, we're ready to start section 5.3, which is on Hamiltonian systems. So I need to start with a definition. If I have a system, so x prime is given as a function of x and y prime is a function of x and a function g of x, y, so it's an autonomous system here. That system has a conserved quantity, h, which is a function of x and y, if h is constant along those solution curves. Okay. So here's a silly example. If I had a system where I had a center and my solutions were just circles centered around the origin, the quantity r, which is just the square root of x squared plus y squared, is constant going around those solution curves. So that radius would be a conserved quantity, because as I travel around the solution curve, that does not change. My location changes, but the value of r, or my distance from the origin, doesn't change. So that would be a conserved quantity. And anytime we have a conserved quantity, the solution curves to that system are just going to be the level curves for h. So that gives me a technique for finding solution curves if there's a conserved quantity. Now that's a big if, but if I know that there's a conserved quantity and I can find a formula for it, the level curves for that function would simply be my solution curves. In this case, notice what we said was conserved was the radius, which is just the square root of x squared plus y squared. The level curves for that would be the square root of x squared plus y squared equals some constant. I could square both sides. X squared plus y squared equals k squared. Either version works. That's going to define for me circles. Okay. So that's what a conserved quantity is and how it can help us in finding solution curves. Now, notice, if this is the case, if h is conserved on my curve, then I know that the derivative of h of x of t, y of t, so h is a function of x and y that's describing a curve in the xy plane, but x and y are functions of t that I get that satisfy this differential equation. If I take the derivative with respect to t of this function composition, that's going to have to equal 0. Again, as time passes, I'm going around these circles, but as time passes, my radius is not changing. So if I took the derivative of the radius, I would get 0 because I'm taking the derivative of a constant. Now, this is going to require a little bit of multivariable calculus. That'll be review for some of you and new for others of you. Okay. We need to take a look at how do I take the derivative of a function composition like this, where I plug in t to get x and y, and then I plug in x and y to get this conserved quantity that we're calling h. And since this is called Hamiltonian Systems, you might guess that we're calling it h because eventually we're going to call that a Hamiltonian function. Okay. So here's how it works. H of xy, this conserved quantity, that's a function of two things, x and y. But each of those things is itself a function of time. So each of these little lines I've drawn in this diagram shows me a dependence relationship in my variables. The value of h depends on y. It also depends on x, so it depends on two things. The value of x depends on t, because x is going to be some function of time. The value of y depends on t. Anytime I have a dependence relationship like this, I also have a derivative, sometimes a full derivative, sometimes a partial derivative, that gives me the rate of change of the output with respect to the input, the thing that depends on the other things. So here, this would be the partial of h with respect to x, would give me the rate of change of h with respect to the input x. And that's a partial derivative there because h depends on two different things. Over here, we would get the partial of h with respect to y. Now here, x depends on just one thing. So if x depends on just one thing, that's going to be a full derivative. dx by dt would measure the rate of change of x with respect to t. Y depends on just t, so that's going to be a full derivative. dy by dt gives me the rate of change of y with respect to t. Okay. So I can do this function composition, plug in t to get x and y, plug that in to get h of xy. These two t's, by the way, are actually the same. If I wanted to, I could have just put t here to say it depends on one thing. I'm sort of in the habit of just drawing it below the x and the y, because sometimes we've got a lot of stuff on the bottom and it just gets a little bit crazy if you don't. But if you prefer to just put a single t here to indicate that that's just one input, that's totally fine. Okay. All right, so I can create this function composition, and when we take the derivatives of a function composition, we use the chain rule, because essentially it's a chain reaction. T affects x and y, which in turn affect h. Okay. Now the way the chain rule works when I've got a situation like this, if I want to get dh by dt, the derivative of my ultimate output with respect to my ultimate input, I'm just going to follow each path that connects them. So there's one path, there's a second path, and along each path I just multiply together the derivatives that we have, and then I add up those paths. So this is the partial of h with respect to x times dx by dt, plus the partial of h with respect to y times dy by dt. Okay. So that's a formula for the derivative of h with respect to t. Now, if h is a conserved quantity, and I plug in the x and y values for some solution to my system, then I know that this derivative would be 0. So I know that the partial of h with respect to x times dx by dt plus the partial of h with respect to y times dy by dt will equal 0. That will be true on the solutions to the system if h is a conserved quantity. Okay. So I want to think about what would need to be true to make this equal 0. Now there are lots of ways that one could make this thing equal to 0, but there's one specific way that is the definition of a Hamiltonian system. That's this. If dx by dt, so if I make this equal to the partial of h with respect to y, and then I'm going to make dy by dt, I'm going to make this be the opposite of the partial of h with respect to x. This feels kind of cheap. But what I've just done, by making this thing equal to the partial of h with respect to y, and this thing the opposite of the partial of h with respect to x, I've made this first thing the product of the two partials, partial of h with respect to x times the partial of h with respect to y. Here, I've just made it the opposite of that product. It's the opposite of the product of h with respect to x and the partial of h with respect to y. If I add something to its opposite, I will get 0. Okay. So, if this is true for some function h of xy, we say the system is Hamiltonian. So if I can show, given a system, if I can show that the derivative functions are actually formulas for a partial derivative and the opposite of a partial derivative for some function h, then I know that that function h is a conserved quantity. My system is Hamiltonian, and the solutions are the level curves for h. So that sort of begs the question, how do I check to see if this is the case? And then if this is the case, how do I go about finding h so that I can find the level curves and I found my solution curves? So that's where we'll pick up in the next video.